Let's move now to the last part. We are going to discuss thrashing. This is actually one of the parts that is usually a bit more complicated. So there is this thing called thrashing. Is something that can happen during your execution, and it's based on the following. If a process does not have enough pages because there are not enough frames that the process can use, then you will have a high number of page faults. Now you know that when you have a page fault, there is this routine to fetch the page, maybe you have to swap out. So when there is a page fault, you start using the disk. And that, of course, has an implication because you have a lot of input-output. What happens is that since the process now is spending more time waiting for reading and writing to the disk than actually running, it starts behaving like an IO-bound process rather than a CPU-bound process, and its CPU consumption goes down. Now, if your operating system is naive and it just assumes that since the process is not using a lot of CPU, then it means that I have free CPU I can use for other processes. What happens is that the scheduler will run more processes, but these processes will also generate a lot of page faults because they will be also fighting to get frames that are not really available. So this degenerates because the more you see that the CPU is not being used, the more you add processes and the less the CPU will be used because also these processes will be fighting for the same frames or the same physical memory that is not enough. And this is what thrashing is. When a process needs frames, okay, and we are of course in global page replacement, it steals from other processes. Then you start having input-output waiting because you have to move the processes into the queues of those waiting for the disk to read and write pages. You think that you can run more stuff because most of the processes are waiting rather than in the ready queue, so you increase even more, but this results in those new processes you want to run to steal frames from the other processes, and this degenerates. So this is the effect on the CPU utilization when you increase the degree of multiprogramming. In the beginning, it gets better, you use more CPU. But if you go above a certain threshold, then the CPU utilization collapses. And this phase here, this part of the graph is where you are entering the thrashing mode, okay? Which means, this might sound strange, but it basically means that sometimes if you want to use more CPU, you should decrease the parallelism degree, okay? Now, how do we know, or how can we know that paging virtual memory is working and we don't end up into thrashing? Well, we have this concept that we discussed before about locality. We said that when we run a process, we are not really using all the pages all the time at the same time, but that during portions of time, we are going to use a subset of pages, maybe the ones that are related to a certain function, and then we move to another function, so we change locality and so on, okay? So if we want to avoid thrashing, what we need to make sure is that the space we have is enough to maintain at the same time all the localities of the processes we are trying to run. It's not about all the space the processes need. It's about the space that is needed by their localities. So this is just an example. This is a graph in which you have the execution time, okay, and then you have a small dot every time a certain process is accessing some of its pages, okay? So what this figure is trying to show you is that you can see that during this portion of time here, pages 18 to 24 here and 30 to 34 are being used, okay? So you see here, this is empty, so it means that that is not part of the current locality because you don't really try to access these pages. But at a certain point here, the locality changes. So now, for example, these 3 pages here are no longer used, and these pages that were not used before, they start being used now. Okay, so you can see that this changing locality over time. So how can the operating system in practice avoid the entering the thrashing mode? One way to go is to using the working set model. So you define a window, a working set window. It's a fixed number of page references. Could be the last 10,000 instructions, for example. Then you keep track, looking only at the last 10,000 instruction, at the set of pages that you are trying to, that is currently being used by the process. And you assume that the locality is, the size of the locality is the size of this set. So here you could have 5 pages, and now you could have 2 pages, or these are 2 different localities. Now, you can imagine that one key question here is how do you decide how big the window should be? Because if you make it too small, then you will not really encompass the entire locality. So you might think that you have space for enough to fit your locality, but actually your locality is bigger, so you don't really have it. On the other hand, if you pick it too big, then you might encompass several localities. And so you might think the opposite. I don't have enough free space because my locality is bigger, but actually no, your locality is not that big. It's just that the window you take is too big. And what you can check is the sum of all the localities, okay, at each point in time. And if this is more than the available frames, then you are clearly entering into the thrashing mode. So in that case, you want to suspend or swap out some of the processes, or at least one of them. So again, challenge here, how do you keep track of the working set? How do you choose the window size? An alternative you can use to the working set model is actually to look at the page fault frequency. So you can define 2 bounds for the frequency with which you can you observe page faults, and you decide whether to allocate or remove frames, and on the long run whether to swap out a process depending on how many page faults you get. Okay, so as long as they stay within the given boundaries, it is okay. If they go above, you can ask for more frames, and below you can release frames. And when you have many that are above, then you can suspend some of them. Now, here you see that you have 2 different alternatives, and actually they are connected. So as always, one of the challenges here is that you don't really know how to choose the window set or the specific number of page faults you can tolerate until you actually start running your operating system and see what processes the user is trying to run, how many of them, how many cores you have available, and so on and so forth. Okay, and here you can also see that there is a direct relationship between the working set and the page fault rate, because what you will see over time, if you just look at the page fault rate, is that usually you start observing an increasing page fault rate when there is a new locality, because the process starts accessing pages that are not loaded right now. Then at a certain point, this peak goes down because now all the pages of that locality have been requested, so they have been swapped in, and for a certain period of time, the page faults will be low because the process is still accessing the same set of pages. They have been loaded. Yeah, some of them might be swapped out because of other processes stealing frames, but the number of page faults remains low. Then all of a sudden it starts growing again because the process is entering a different locality, and so on. So actually, if you want to find an approximation of how big the working set could be or should be to be the correct one, then you can monitor the rate with which you observe page faults in your operating system. But as you can see, this now becomes complicated because of this relationship between the 2 measures.